Hello, everyone. Welcome to the next lecture of electronic devices. We are covering chapter number 1 of the book, and this is the lecture number 4. Okay, so in today's lecture, we are going to talk about circuit model of amplifiers. So what we will do in this lecture, we are going to first make an equivalent electrical model of an amplifier. We will try to see what are its terminal characteristics and then we will see what are the different design considerations in terms of what are the ideal characteristics of an amplifier, or what are the characteristics of a good amplifier. So this is what we are going to talk about in detail in this lecture today. So importantly, the first thing is, why do we need a circuit model, right? So why do we need a circuit model? So amplifiers are used as a building block in designing big electronic systems. You are going to realize that sorry, the amplifier is kind of a very one of the fundamental building blocks in many of the instrumentations, electronic systems, even in medical instruments, right? You're definitely gonna find a amplifier there in the EKGs, EEG instruments. So in a lot of medical instruments as well, amplifiers are a building block because it happens a lot that the signals that we acquire are usually very small, and then we want to amplify the signal out of it. So it's a good idea to make a circuit model of an amplifier and see its terminal characteristics. Right, so in this lecture we are going to model the amplifier and see the terminal behavior, right? So we will model the amplifier and look at terminal characteristics. So terminal characteristics are the characteristics for at the input and the outputs. Okay, so if you guys remember, this was the model of an amplifier that we drew, right? And this is with a common ground. And we said that this is a two-port network. Here's an input and here's an output. Now let's add more details to it in terms of developing an equivalent electrical circuit. Or let's look at what is essentially inside this triangle. So if I have to make a more detailed model of an amplifier, this is how it looks like, and I am going to explain this just in a bit. So this Ri is the internal resistance of the amplifier, and Vi is the potential drop across that internal resistance. R0, this R0 is the output resistance of an amplifier, and this is a voltage dependent voltage source. AV0 is the gain factor, and it is controlled by the input voltage Vi. Okay, so this is the what's inside that triangle, right? I can also draw the same thing here. So this is what it is, or essentially, yeah. Okay, so our Ri is the input resistance of an amplifier. R0 is the output resistance of an amplifier. And then we have this, and then our, right, so this was our voltage control, voltage source, voltage controlled voltage source, and the gain factor is, right, so this is controlled by the input voltage Vi, and here's the AV naught is the gain factor with the gain factor of AV naught. All right, so by now what we have done is we have made an equivalent circuit of the amplifier, right? So this was the circuit model of an amplifier. So essentially, yeah, this is the entire description, actually, more like this. So it has an input resistance Ri, that is the input resistance of the amplifier, and there is going to be a voltage drop across it, which is Vi, and then what else is inside the amplifier, since it is going to amplify the signal, so there should be a gain. And so this this is a voltage controlled voltage source in the amplifier, which is going to which essentially indicates over here is that it is being controlled by the input voltage Vi, and it is going to amplify the signal with a gain factor of AV naught, and R naught is the output resistance of that amplifier. Okay, now what we will do now is we are going to take this circuit, and now we are going to connect the input, whatever the input that we want to amplify, and we are going to connect the load resistance. And then we will look at, then we are going to drive certain equations. Okay, now let me make the circuit again, once again. Okay, so I have, I just, this, right, so this was R naught, this was AV naught Vi, Ri Vi, right, and this I'm just going to explain this just in a second. Again, the dotted region over here, the dotted rectangle shows the inside of an amplifier, or the equivalent circuit model of an amplifier. So what we did now is we connected the input that we want to amplify. This is indicated over here by Vs. Vs is a source voltage that we want to amplify, and this source has a resistance Rs. So this is what we have connected to the input of an amplifier. What we have connected at the output of an amplifier, right? So we talked about this. This port is the input port, and this port is the output port. What we have connected at the output is the load resistance RL, and the potential drop across the load resistance is going to be V naught. Another thing will be the current that will be delivered to the load resistance is going to be I naught, and the current that will be drawn from the source voltage will be II. All right, now let's look at the terminal characteristics of the of this model. We are going to see more details now. So let's first start with what is the input voltage of amplifier, right? So input voltage of amplifier is Vi. So can we find the equation for that? So the Vi input voltage over here, so we are interested in finding out this value Vi. Vi can be easily found out by using a voltage divider rule at the input, right? So Vi equals the source voltage into input resistance Ri over Ri plus Rs. Okay, so this is good. We can just use a voltage divider rule. Okay, now what we are going to do is output voltage of an amplifier V naught. So now we can apply, now in order to find out this output voltage, we can apply again the voltage divider rule at the output. So the V naught is going to be the voltages sources AV naught VI into RL over RL plus R naught. So this is a value of the output voltage of the amplifier. Okay, now let's find out the voltage gain of the amplifier. So what is the voltage gain of an amplifier? We are going to define two different gains. One is a voltage gain of an amplifier, which depends on the input voltage here and the output voltage V naught. And then we are going to define another voltage gain, which we are going to call as an overall voltage gain that depends on, in which the output is going to be still V naught across the load resistance. However, our input is going to be not the input of an amplifier, it will be the input voltage that we have applied Vs. So we are going to find out both. Okay, so first let's find out the voltage gain of an amplifier. We are going to call AV, and AV will be equals to V naught over VI. So this is equals to the, so this V naught over VI is the voltage gain of an amplifier. Okay, so the voltage gain of an amplifier V naught over VI, I can easily see it from this equation. I can rewrite this equation over here. So V naught VI can go over here, right? So V naught over VI can be equals to AV naught into RL over RL plus R naught. So this is the voltage gain of an amplifier. Now, interestingly, the one thing that we can see from here is, okay, so the one thing that we can see from here is if R naught here equals to 0, right? If R naught over here will become equals to 0, this means that our AV voltage gain of an amplifier will becomes equal to the AV naught, which is the voltage gain of an amplifier in the open circuit condition. We're going to just talk about that in more detail. What exactly is AV naught? So essentially what this R naught was doing is, it was, if I look at this equation, right, so what this R naught factor was doing is, it was kind of decreasing my voltage gain, right, AV. So if the smaller my output resistance will be, there will be less decrease in my gain compared to the AV naught. Okay. Now, so second thing that I want to talk about over here is that now if load resistance approaches to infinite, which means that we have an open circuit at the output. Open circuit. If RL approaches to infinite, then again AV will become equals to AV naught. So AV naught is also known as open circuit voltage gain. All right. So one thing is that AV naught is an open circuit voltage gain, considering that when RL is infinite, means that we have an open circuit at the output, the voltage gain of the amplifier is equals to the AV naught, right? So that is why it's called as an open circuit voltage gain. Now, what happens is, ideally we want, and we're going to talk about this just in a bit again, but our while designing the amplifier, we want to make sure that the output resistance of the amplifier should be as small as possible, and ideally 0, so that our gain of the amplifier should be as close as possible to the open circuit voltage gain, and we should not get a decrease in the gain factor. All right, so we ended up talking about it. Okay, so the other gain that I want to talk about now is the overall voltage gain. Overall voltage gain. Overall voltage gain, capital AV, can be rewritten as our output of the amplifier divided by the source that we have connected that we want to amplify. I can rewrite this equation as V naught over Vi multiplied by Vi over Vs. So V naught over Vi and Vi over Vs. V naught over Vi is coming from here, and now Vi over Vs can come from this equation 1. Right, so we can, all right, so V naught over Vi is AV naught into RL over RL plus R naught, and Vi over Vs will be equals to, is going to come from this equation, equation number 1, which will be equals to Ri over Ri plus Rs. So this is the other gain, which is known as the overall voltage gain. Please understand and memorize this difference. There are essentially 2 or 3, you can say 3 types of gains. The first type of a gain is this open circuit voltage gain, in which is usually the gain of the amplifier when no load resistance is connected. The second gain of the amplifier is the gain of the amplifier neglecting the source that we have connected that we wanted to amplify, and which is equals to the output voltage. I'm sorry. Right, so which is equal to the output voltage and the input voltage drop at the input of the amplifier Vi across the resistance, input resistance of the amplifier. And the third is the overall voltage gain. Overall voltage gain is the output of the amplifier divided by the source that we have connected to the amplifier. So there are 3 types of different gains. Okay. Now the third thing that we will, so we have derived all of these equations. This is a very simple modeling of an amplifier. The third thing that we want to do before we wrap up this lecture is we want to kind of describe the different design considerations. Design considerations, or you can say criteria for a good and ideal amplifier. So we want to come up with a criteria of what a good amplifier, what are the criteria for a good amplifier. Mostly whenever we are saying that we are designing an electronic system, sometimes it relates to how you are selecting the different resistance values, right? So we already touched upon to a certain extent this concept in this slide, right? When we were talking about that our output resistance should be smaller so that we don't have a loss in the gain. So this is one of the criteria. So I'm going to talk about this thing again. All right. So design considerations. So the first design consideration is that our input resistance should be extremely larger than the source resistance, right? Now, so we know that our equation 1 is Vi equals Vs into Ri over Ri plus Rs. So let me go back in this slide. So this was that equation. So this is the input voltage, right? So please see over here, what is the Vi? Vi is the voltage drop across the resistance Ri. So what do we want? We want the Vi to be as similar as Vs. Ideally, we want Ri to be open circuit or to be infinite, so that we don't have a voltage drop here at all. So what we want is, we want our Vi, or essentially Vs, to be amplified without any loss in the signal. So the first loss that is happening is just because of the coupling of the source to the input of the amplifier due to the Ri. So if the higher the Ri, the smaller the loss will be. All right. So in order not to lose significant portion of input signal in coupling input Vs here to amplifier input, right? So for if input resistance is very extremely larger than the source resistance in this equation, this will make sure that our Vi will become equals to Vs and there will be no loss in the signature. For ideal amplifier, input resistance is infinite, right? So what we want is, again, let me tell this again, that we had two resistances at the input. Looking at the circuit again over here, right? So one is a source resistance, one is a input resistance of the amplifier. So that is under the dotted rectangle. So what we want is, we want to make sure that the Ri should be as large as possible and ideally infinite, so that when we connect the Vs to the input of the amplifier, we do not have a drop in the voltage signature, and we have all the voltage available Vs to be amplified. So this is the important criteria. The input of the amplifier should have as high of the impedance as possible for to prevent the loss in the electrical signature. All right. Second design consideration now, our R0 should be as small as possible than the load resistance. Now if I write the output voltage at the amplifier, I'm kind of rewriting this equation. So that was a voltage value plus R0. Again, this equation is coming from here, right? So this was equation AV0 VI RL over RL plus R0, AV0 VI RL plus R0. So what we want, now let's look back at the circuit. Why do we need a very small R0 as compared to the RL, right? Going back to the circuit again, what we want is, we want this resistance to be as small as possible and ideally even zero, so that all the potential drop will happen across the load resistance that we want, right? So that is why we want the R0 here to be as small as possible than the load resistance and ideally zero. Right, so over here, not to lose gain in coupling amplifier output to a load. All right, so these are the two main design criteria for designing an amplifier. So one is that our input resistance should be as large as possible than the source resistance, and the second is our output resistance should be as small as possible compared to the load resistance. There's one more concept that we're going to talk about, and then we will finish the lecture today, and that concept is buffer amplifier. You're going to come across this multiple times during the course. So we're here, we are going to very quickly introduce this this concept and then move on, right? So now let's consider an example. So we have input source. Let's suppose that we have our input source has a reasonable voltage, right? Let's suppose I have a system, I have an input source, but it has a reasonable voltage that does not need any amplification. But the source, however, source resistance, the resistance Rs of this input source is much larger than load resistance, right? So for example, what is happening here? For example, this was your Vs, this is your Rs, and this is your RL. So now the problem over here is, let's suppose we don't want the amplification to be done. Our Vs is reasonably okay. We don't want the voltage amplification at all here. But the problem that we have is our source resistance, our Rs here, is significantly larger than load resistance. When this will happen, you can realize what this is happening. When this will happen, this means that if I will connect this source to the load, the signal will attenuate. Most of the potential drop is going to happen across Rs, and very small potential drop is going to happen across RL. Right? So if we connect source to load here, signal will be significantly attenuated, right? And this is what we don't want. Although we don't need an amplification here because we believe Vs is sufficiently okay. The problem is when we connect this source to the load, we lost a lot of that signal because our source resistance was very high as compared to the load resistance. Right? So in order to solve this problem, what we do is, to solve this, we use a buffer amplifier. So what is a buffer amplifier? Buffer amplifier has the same characteristics as an amplifier. The input resistance is going to be very high and the output resistance is going to be very small. The only difference is that the gain of that amplifier is almost equals to unity, right? So buffer amplifier gain almost unity. So what will happen is, now we will connect the source Vs input source to buffer amplifier. So buffer amplifier's input resistance is very significantly larger than the source resistance, so we will not have a potential drop. And unity gain, since we don't need a voltage amplification because our values of the Vs is sufficiently okay, and our output resistance is very smaller than the load resistance, so this will ensure that our Vs will be available at the load resistance without signal attenuation. Right, so this is why we use a buffer amplifier, and you are going to realize that we use buffer amplifiers every now and then in a lot of these different circuit wild circuit designs and different applications. Okay, so with that, we are going to finish the lecture. In this lecture, we started with developing a circuit model of an amplifier. We saw that what's inside a circuit model here of the amplifier. It has an input resistance, an output resistance, a voltage controlled voltage source. Then we write down the terminal voltages of that amplifier, the input voltage, the output voltage. We define 3 different gains: the open circuit voltage gain, the voltage gain of an amplifier with respect to the input voltage at the amplifier input across the input resistance of the amplifier, and then we define the overall voltage gain, which is the voltage gain with respect to the source voltage that we have connected. We also saw that in order to design a very good and an ideal amplifier, our input resistance of the amplifier should be sufficiently larger, ideally infinite, and our output resistance should be sufficiently significantly or sufficiently smaller than the load resistance. And finally, we talked about a buffer amplifier, that if we have a source which has a reasonable voltage, that we do not want a voltage gain here. We don't want the voltage to be amplified. The only problem is we cannot directly connect it to the load because the resistance of the source is very, very larger than the load. So what we do is we connect it to a buffer amplifier, which is a regular amplifier with a very high input resistance compared to the source and a very low output resistance compared to the load. However, the gain is unity because we don't care about the amplification. Our voltage values are sufficiently good. Okay, so with that, we are going to wrap our lecture today. In the next lecture, I am going to talk about cascaded amplifiers, how we can connect multiple amplifiers together to develop a system, or a cascaded amplifier system. We will do another example problem to see how we can solve these circuits based on the circuit model of an amplifier, in a cascaded model, especially the example we will do. And we will also talk about a couple of other amplifier examples, or circuit models. All right, so with that, thank you so much. I will talk with you in the next lecture. Have a good rest of the day. Bye-bye.